Alright, geometry scholars, here's my little video of what you should study for the test, what to be concerned about, and some examples. Alright, so here's a list of things. You can refer back to this sort of beginning page later if you want to. I think everything here is pretty much self-explanatory. You'll see what I mean by how difficult it gets as we get into it. So let's get started. Here's where to look for review things. In reference to those things that were just on that front page, there's two types of problems with the a plus b bigger than c, and by that I mean the triangle inequality. You know, that was the one where in any triangle, you know that any two sides have to add up to be bigger than the third side. There's two types of problems in that. One type of problem is, can this be a triangle? In other words, I'll give you, like, I don't know, I'm not going to have enough room if I keep doing this here. Let me put a new page in. You know, they'll give you three numbers, and I'll say 3, 4, and 6. Can that be a triangle? Is your question. Is it possible that a triangle has sides 3, 4, 6, and it's a yes, no question? And this one would be yes, because all you have to do is check and make sure that the three inequalities work. Technically speaking, we were thinking about 3 plus 4 being bigger than 6. 4 plus 6 has to be bigger than, not equal to. And the last way to do that is this way, and since all three of those are true, then it's yes. You might get one that's slightly crazier, like a half, 3/4, and oh, let's make one really nutso here, 7/6. Is that going to be possible? Well, you have to check, is 1/2 plus 7/6 bigger than 3/4? Is 3/4 plus 7/6 bigger than half? And is 1/2 plus 3/4 bigger than 7/6, and that's the one to worry about. Usually it's are the two smaller ones big enough to be bigger than the third. You could decimalize this, but we're really concerned about, you know, is this going to happen? And sometimes it's no, right? We're asking ourselves, is that true? This is 1/2 plus 3/4, that's like 5/4, right? And now we get into this kind of situation. Which one's bigger? 5/4 or 7/6? I'm pretty sure 5/4 is bigger. Okay, example of how that could be no. 1, 2, 3. So this is a yes. 1, 2, 3 is a no because 1 plus 2 equals 3. 1 plus 2, the check is it greater than 3? And this is no, because it can't be equal to. It has to be strictly greater than. Then of course another really bad one would be something like 5, 6, 18. There's no way, because 5 plus 6, checking out that it's bigger than 18. This is also a no. Okay, so that type of question. Oh, sorry, that was one type of question on this kind of thing. The other type of question on that kind of thing is, if you have a triangle and you know two of the sides, let's do the 5 and 6 again, why not? What are the possible possibilities for the third side? We know this x, has to be a number such that 5 plus 6 is bigger than it plus 5 is bigger than 6, and 6 plus it is bigger than 5. One of those doesn't really make sense at all, but the trick on these is, actually I'll write that up. 5 plus x has to be bigger than 6, that's kind of interesting. 5 plus 6 has to be bigger than x. The other one, think about this, 6 plus x has to be bigger than 5, that's kind of silly because 6 is already bigger than 5. But these two lead to some interesting places. X is bigger than 1, and 11 is bigger than x. Whoops, I said x. 11 is bigger than x. That kind of means that we know x has to be between 1 and 11. How do you do that quickly? You'll notice here that 1 is the difference of 5 and 6, and 11 is the sum of 5 and 6. So yeah, this usually works out to just kind of take those two given numbers for these limits, subtract them, 6 minus 5 for one end, and 6 plus 5 for the other end. You'll see that always works. And again, make sure to put strictly less thans in here. No less than or equal to. Equal to doesn't work. Alright, corresponding stuff in similarity statements. When you make a statement like, this will just fit here. When you make a statement like triangle ABC is similar to triangle DEF, make sure, what that implies is that yes, angle A goes with angle D, angle B goes with angle E, angle C goes with angle F. Side AC, for example, is corresponding with side DF in the other figure. And that is true. I mean, you gotta be careful about that, whether we're talking about triangles or pentagons or whatever. Although there are no proofs on this test, you will have to be able to justify whether or not triangles are similar. And there are only 3 of them, so there's 3 ways to justify. Let's tell you what they are here. Angle was the postulate, and then there were 2 theorems, side, 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 and side, angle, side. fairly straightforward how those are the three. And there might be some answers to that question that could actually be, it could be no. You're going to get some questions like, oh, here, let me do another one of these. You get some questions like, here's a triangle, here's another triangle, you know some stuff, but you don't know everything. Like, you maybe know that, this is 6 and this is 3 and this is 10 and this is 5. Are these triangles similar? Well, I see two sides and an angle here. Maybe it's side angle side that makes these things similar, but wait a second, we don't have side angle side. They're not in the right places. That would have worked if we would have known about a different angle. Whoa, I didn't mean to mute everything. If we had a different angle, if we had, instead of this angle, if what we knew was this one, now it might be side angle side. Side angle side is still a good candidate now because we've got two sides and an angle between them. We have to check, are they really proportional? Does 5 go with 10 like 3 goes with 6? That's a 3. 3 goes with 6, and it turns out that they do. They both equal half, so we're in good shape. So be careful about that kind of trick. That will happen to you. Proportion ratio properties like page 225. 245. Be on the look for sideways but legal. What are we talking about? Legal moves that they make in a proportion. I'm talking about that purple box in the middle of 245. They do stuff like they'll say, okay, if A over B equals C over D, then you can actually imply, or that kind of means the same thing as adding the stuff. That's the one that always gets people. A plus C over B plus D equals either one of those things. Actually, I could just change this into an equal sign. Yeah, I mean, this is equal to those also. I don't know. That's not going to be a huge deal in the test. And this, by sideways, I mean this is the same thing as, now these fractions won't be equal to this, but if you know A over B equals C over D, you can also write that as A over C equals B over D. Those little manipulations are nice to be familiar with. All theorems from, like do now, that's referring to my class. I had some of those in the beginning of my class one day to do now. All theorems from chapter 7, including these. The wacky theorem about the angle bisector of a triangle. That's the one that I think is going to get the most people. People forget about it. You got a triangle and you take an angle bisector at one of the corners. If that's a bisector, what ends up happening is, it cuts this opposite side into two chunks, and you have a similarity kind of situation here and here with the two parts that it cuts it into. In other words, A over B equals C over D, and sometimes those are hard to find, and it's also hard because it's hard to believe that that's always true, but it sure is. A over B, and there's no similar triangles in this picture. It's another one that. That's why it kind of trips people up. So that one, just don't forget that it's there because it's kind of a big deal, but it's kind of hard to remember. The one about parallel line and triangle and the parts, by that I mean if you had a triangle and some parallel line in there, the parts, not to be confused with the holes here, A over B equals C over D, you can say A over B equals C over D. You can't say, this is where it's going to get people. You can't say something like A over B equals X over Y, because B, mainly it's B's fault here. B is not a side of the triangle, so this is illegal. If you were going to try to find Y here and you knew everything else, what you could do is say, well, A is to X like the entire side of the triangle is to Y, and the entire side of the triangle is actually A plus B. So you just have to be careful there that you use entire sides of triangles, but that is could certainly be part of the same picture and same situation as the one where you can use the parts. That's one of the weird theorems, and any proportion problem that I've just been talking about may not all just be numbers. There might be something crazy in here, like this could be 2x minus 4, and this could be x squared plus 2. We could go to town on that because we did spend a couple of days on some of that difficult algebra at the beginning of this unit. Some other things to think about as you review, where to look. Properties of a dilation and how to read a dilation. Dilations need a center, just like rotations actually, and they also need a magnitude. Sometimes we call that, it's really hard to write this fast enough. Usually we call the center, you know, a lot of times in coordinates it was the origin. Usually it's like a center, like I use the center point P a lot in mine. A lot of times in the book it's point O, but there's a center point where everything kind of explodes from or gets contracted to, like sucked into the center of the universe there, because it's the center of the dilation. This is the place on the dilation, if you're doing it with a ruler, where you always put your 0. So it's kind of thought of as the 0 point. Magnitude is a number. It's the multiplier. Most times in the book, and when I do my examples, I use the letter K for that. It's the multiplier you use to change the before and after sort of translation between the two different scales. And if that number is greater than 1, we call it an expansion. If that number is less than 1, we call it a contraction. And you kind of should know how they look when something is expanding versus contracting. And also realize that we did not talk about any values of K that were negative. K was always greater than 0. And it's at 1 where things get interesting. At 1, it wouldn't do anything. Before 1, it's a contraction. So numbers like 3/4 or half or a third. The objects are going to get smaller and drawn in towards the center, and expansions, they fly away from the center and get bigger. That could happen on coordinates. The center may or may not be the origin, so be careful of that. And different types of word problems. There was a lot of these in the book where they had a sun and a shadow, and you had to figure out usually the height of something taller than you. There was the U and there was the unknown height, but you knew the heights of, you knew the lengths of the stuff on the ground. Be careful. That one kind of reminds me of, a couple pages back now here. It kind of reminds me of that one I was just talking about with the parts and the hole on the this kind of triangle. Because if you had a triangle with heights, first of all, you're supposed to kind of justify that, yes, these are similar by AA. The angle of the sun's the same in both, and the heights are measured as straight up. But this little piece here and this little piece here, especially this little piece, this is like the B kind of problem we had over here. This is not a side of the large triangle, so be careful. Actually, this would be more like the B, wouldn't it? Anyway, one of these is a side of a triangle, and this is a side of the triangle. So don't get. How do I put some numbers in here? If you had a 2 and a 5 here, you have to realize that a lot of times you're going to want to use the 7 as the side of a triangle and not the 5. Of course, the 2 was a side of the smaller triangle. Okay, and ladder wall problems. There's the height of you have a ladder resting against a wall, and you know how far back this is, and you know how high the ladder reaches up the wall, maybe. And you have a similar triangle inside here, something like that. So that's a lot the same. There were some mirror-y ones in the book too, where you're like looking at the top of the tree in the mirror, and it tells you that this creates the same angle here, so you have similar triangles like that. So just word problems. There may or may not be a diagram for that. Ratio and scale problems, which may or may not have anything to do with geometry. If you were building a model car, and they tell you that the model car, and this is a common one I think they use, is a 1:18 scale car, and you knew that on your little model, again, there'd be no picture in the thing, don't make fun of me again, you knew like the diameter of this wheel here was exactly 1.1 inches. The question might say, well, in the real life car, how big is the wheel? That would be a simple ratio problem. That's why this could be done without you. It's hard to read that 1.1. Without you knowing anything, without seeing a picture at all. And all you gotta do is, okay, I know this scale is 1/18. So anything, while comparing this to this, is going to be in the same ratio as 1 inch here represents 18 inches in real life. So 1/18 is going to have to equal, okay, we have model to real life equals model to real life, and I could figure that out that way. All right, performing an actual dilation, I'm going to use K equals 3, and first you have to decide whether that's it. You may be asked, is that an expansion or a contraction? I'll start here with point A. Yeah, always measure from center point P. That's the center of the dilation, has to be where the 0 goes in your ruler. You measure this to A, you multiply by K, and here 25 times 3 is 75, so right around there is where I'm going to draw A prime. Maybe. Oh, I was drawing the ruler. A prime. I do the same thing. It's right there. Let's do the same thing for Q. I start with center point P, leave the ruler there. People are accidentally putting the 0 on Q sometimes, and with a contraction, that can really be a problem. 65 times 3 is, I need a longer ruler. 65 times 3 is 195. I'm going to have to cut this short because I want to get done before 15 minutes. I would do all 4 and connect the dots. Okay, and in 12 seconds, I'm just going to leave it on this frame. You can pause and look at this for a second, how I did this. This is what I meant by the difficult kind of algebra. It may be a little bit harder than this, but not much. Okay, good luck.